Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're doing the Work-Energy Theorem, and we're doing it in our revolutionary science teaching way. So here we used a little Lego car in a previous video, and if one pushes the car, you see that it very quickly comes to a halt. So in other words, it's got quite a lot of friction, and I thought for fun and for the sake of this experiment, let's roll the cart down a slope and measure how far it takes for it to come to a halt, and then we can deal with the whole work-energy theorem this way. So let's make a mark here, and we're going to roll this down the slope and see where it ends up. So here there's a pointer, and here is where it came to a halt. Let's do it again a few times just to see if it always reaches the same spot. Exactly 1 or 2 mils different. And one last time. Oh, okay, so that time it was about 3 centimeters short. Let's just do it once more. And there, that was within a whisker. So 1, 2, 3 of the marks are almost together. So let's say that for this one, it probably, as it came down this bump, maybe something disrupted it. So it looks like the most 3 marks almost together within 10 or 12 millimeters. So let's take that as our distance. So now I've got my tape measure, and I'm going to measure the distance from the start to the average midpoint at the end. So if we take that as our there, so that was 31, 114, 1.14 meters or 114 centimeters. Now let's familiarize ourselves with our formulae. So we go to our BFF, or best physics friend, our data sheet. Because you haven't got one, I've written out the formulae, and here are all the formulae that are related to this problem. And let's relate them. So we're going to see that we're going to do some work on this trolley, and we're going to do it in 2 forms. It's going to fall down the hill. Now that is going to be what we call positive work, and it's going down the hill. What's going to add positive work to it is going to be in this direction. So although it's not a vector, but we can still say that that direction, any force that acts in the direction it's moving, we're going to call a positive work. It's not strictly a vector, because every single one of these things is a scalar quantity. It's energy. They're all measured in joules. Work net delta K is change of kinetic energy. So as this goes down the hill, it starts with no kinetic energy, gains kinetic energy, and then it comes to a halt and loses its kinetic energy again. So from the start to the end, there's no change of kinetic energy. Then we have something called work that is non-conserved, or non-conservative forces, friction in other words. This is frictional work. So acting on the trolley is going to be a force of friction, and it's going to be in that direction, force of friction, and that force of friction is going to do what we call negative work on it, non-conserved work. Then we have change of kinetic energy. So from here, no kinetic energy. Here it's moving, and kinetic energy is half mv squared. The mass is not going to change, half is not going to change, but the velocity is going to change. So only the velocity is going to change. And then here we have delta U, that's change of potential energy. Now what is potential energy? Well, U is mgh. So potential energy, what gives it potential to move fast down the slope? Well, it's got mass mass, which we remember was 0.35 kilograms, and gravity pulls on it, so we've got G equals 9,8, and it's got a vertical height that it falls coming down the slope, and that is a height, I measured it, of 6,5 centimeters, or 0.065 meters. And then there's change of kinetic energy is final minus initial. Final's naught, initial's naught, so the change of kinetic energy in this particular problem from start to finish is 0. So that we can remember. And then in general, work done is force times distance, and then cos theta gives it a sign. Now cos theta, if this is our direction that the trolley's moving, if your force is acting opposite to it, then theta is that angle between the direction it's moving and the direction that the force is. So in the case of friction or work NC, it's going to be equal to, this cos theta will be cos 180, because frictional force acts at 180 to the direction of movement. So there we go. So now we're familiar with all the terms, and we're going to use what is called, this formula is called the Work-Energy Theorem. Now, this is what the learners have to remember. Net work is change of kinetic energy. And then they'll ask them to quote it because they're going to use it. And in all questions on this, you use this formula. So what net work do we do on this trolley? We know the change of kinetic energy. It starts at naught, it ends at naught. There's no kinetic energy. What work do we do? Well, there's two forms of work we're going to do. There's a coming down, the work, force of gravity times the height, and that's a positive work. And then we're going to have frictional work, so that we've only got two things, two works that we have to add up to, and they've got to add up to, in this case, 0. So the one is a positive work, which is the force of gravity times height, which is mass times g is a force of weight, mg is weight, there's weight, we could say a force of weight, delta h is vertical height, or delta x is equal to h. So those two equal that, those three. And then the cos theta just tells us if it's a positive or negative work. And in the case of gravity, it is acting in the direction down the slope. Now, does it matter that our slope is at an angle, or would it make any difference if our trolley went straight down and then did that? Well, in physics, it doesn't matter, because in this case, this is what we call a conservative force. It doesn't matter what path you take, whether you go straight down and then go right, or you have a slope, or you have a steep slope, steep but short slope. The only thing that matters is the h, which is vertical height. So the path that it takes does not matter. So as long as we know it started, the 6,5 was actually from there I measured, not that height, but from there to there, that is the 6,5. So let's just correct that. That is there. That height is 6,5 centimeters, or 0.065 meters. So if we add friction, which is negative, to mgh, which is positive, the two should add up to 0. So what are we going to do? Work net means add up all the forces that act on the object during the course of its travels, and they must all equal to the change of kinetic energy of the trolley. So what two forces did we have? Let's give them. So we're going to get the work NC, otherwise known as friction, and the work due to, which is we can call mgh, or change of mgh, and those are all going to add up to delta k, change of kinetic energy. So we'll start with that formula. Then we've got our two works. Now what is the frictional work going to be? It's going to be force times delta x, distance that it traveled, times cos 180 plus work due to mgh, which is going to be mass 0,35 times g 9,8 times vertical height 0,065 meters. Let's just get ourselves some space here. So there's the frictional work, and there's the work that is positive work done in the direction. Now we could say, because m and g is equal to a force and h is a distance, we could also actually add times cos naught. Why? Because gravity is acting in the direction which the trolley is moving. And we said it doesn't matter if the trolley falls straight down and then goes that way, or if it's at a slant. Only thing that matters is vertical height, and the cos theta is in the direction of the vertical height. So we know that all of that work must add up to a positive number, and this here, frictional work, must be a negative number. So if we take we're trying to find the frictional force, times we know the distance, we know cos 180, which is going to be -1. We know the mass, which is 0.35 kilograms. We know g is 9,8. We know h is 0,065. We know that we're going cos of naught, which is going to be 1. So all of that is going to be a positive number. That's going to be a negative number. And then all of that adds up to change of kinetic energy equals change of kinetic energy, which is equal to final, which we know is naught, and initial is naught. So the change of kinetic energy is equal to naught. And then we solve for force. And that will give us our frictional force. Now at that stage, I would just let the learners go ahead and solve it for themselves, as long as they know how to do it. So here we've done the maths. Frictional force times 1.14 meters times -1 plus all of that mgh adds up to 0,22295 equals naught. So frictional force times -1,14 equals that equals naught, plus that equals naught. So if we take that to the other side, it becomes minus that. Divide both sides by -1,14. Those cancel out, leaving us with minus 0,22295 divided by -1,14. And therefore, when we divide that into that, frictional force is equal to 0,2 newtons. 0,2 newtons was the frictional force of that buggy.